Thank you for joining. I'm Nigel, a PhD student at the University of Massachusetts Amherst, advised by Professor Andrew Lan. I'm excited to present our work accepted at EMNLP 2024, introducing DiVERT, a variational approach for distractor generation for math multiple choice questions by learning to represent errors as interpretable text tokens. Multiple choice questions are arguably the most common assessment format. Each MCQ contains a question stem and a series of options, including the key, the correct answer, embedded among several other distractors, the incorrect answers. Our data also contains teacher-written error explanations, that is an explanation of the error made by a student when choosing a particular distractor. A good set of distractors should not be too obvious and should ideally correspond to errors in the factual recall or reasoning process made by a student. Constructing good distractors usually relies on extensive teacher effort, which motivates the need of automated approaches. To maximize the learning gain of students, being able to interpret the cause of error behind a distractor is highly important. We introduced DiVERT, a novel variational approach to jointly learn error representations in math MCQs, as well as generate distractors corresponding to these errors. We conduct experiments on math MCQs shared by ED, a leading math education company with content used by millions of students. DiVERT, despite using a base open source LLM of just 7 billion parameters, outperforms GPT-4o on distractor generation. We also identify a direction of future work in improving LLM consistency in following instructions with flawed reasoning. Let's introduce some notation. An MCQ denoted as Q contains a set of textual components, the question stem S, the key K, an optional explanation of the key EK, a set of distractors D, and a set of error explanations E behind these distractors. All these components are interpretable text or math tokens. Our goal is controllable, explainable distractor generation. We first need to generate plausible errors as text descriptions given the question stem and key. We then need to generate the distractor corresponding to an error. There can be numerous possible errors among real students for each math MCQ, all of which may lead to different distractors. Without explicit error annotations, an error is a latent variable underlying a distractor. Thus, the likelihood of a distractor given a question stem can be computed as follows, where we sum over the space of all possible latent errors, which can be computationally intractable. Given this perspective, we naturally use a variational approach to learn an approximation of the large latent error space. We jointly learn the latent distribution and maximize the data log likelihood by maximizing the evidence lower bound, as shown. Here, PE given S generates a textual error description given a question stem. PD given SE generates the distractor as a result of an error. QE given SD is our variational model from which we sample errors behind a question distractor pair. There can be many choices for the variational distribution Q. We choose this form since it's intuitive and can also be useful in practice to recover errors from distractors. Our variational pipeline parameterizes the three components as three separate LLMs. Since we choose to represent errors as discrete text tokens for interpretability, we use a soft token-based differentiable learning approach to enable gradient flow between the LLMs. During generation, we use an overgenerate and rank approach by first generating errors using diverse beam search, then generating corresponding distractors using beam search, and finally selecting the top K distractors with highest beam scores. Let's visualize the process in DiVERT. During inference, given a question stem, we first generate a plausible error, followed by generating the plausible distractor. During training, to approximate the large latent error space, we sample errors from the variational model Q, represented as discrete text tokens for interpretability. To enable gradient flow, we use soft tokens. Each discrete one-hot token is simply converted to logits-weighted text embeddings. We find using an annealing process for the temperature of this approximation helps. The variational error identifier model, Q, is coupled with the error generator model, PE given S, through the KL divergence loss. We work with a real-world math MCQ dataset from the ED Learning platform, containing MCQs on 41 unique subtopics, including basic arithmetic, fractions, and solving equations. We collect error labels for each question distractor pair from middle school math teachers. To evaluate distractor generation, we use alignment-based metrics comparing against teacher-authored distractors. Exact match checks if all distractors match. Partial match checks if at least one of the generated distractors match. Proportional checks the fraction of ones that match. Since the 3 ground truth distractors for a question could be incomplete, we also allow 10 distractors to be generated per question, similar to a map at K approach. We find these at 10 metrics to be more robust, especially proportional at 10. The open-ended and mathematical nature of errors makes automated text similarity metrics unsuitable for error evaluation, and we instead perform a human evaluation. We compare DiVERT to state-of-the-art distractor generation approaches from prior work. For prompting baselines based on GPT-4o, we compare against zero-shot chain of thought, where GPT-4o first generates errors before generating distractors. We also compare against KNN with in-context learning, where the 3 most similar MCQs containing error labels behind their distractors are used as in-context examples. We compare against 3 strong fine-tuning baselines: directly generating the distractor given a question stem, generating a chain of thought error before generating the distractor, and a 2-step pipeline like DiVERT, first generating errors followed by generating corresponding distractors. Our results show that DiVERT, despite using a much smaller base open source LLM of 7 billion parameters, MetaMath Mistral 7b, performs on par with GPT-4o and outperforms other baselines on the more robust at-10 metrics. We also find using errors as chain of thought supervision improves downstream distractor generation performance. Collecting error labels from teachers for question distractor pairs is laborious. We find that DiVERT works even with a small number of error labels and outperforms other baselines as the number of error labels decreases. DiVERT shines by leveraging its variational approach to sample errors from unlabeled question distractor pairs during training. In this qualitative example, we find DiVERT prioritizes plausible errors among real students and generates corresponding distractors. We recruited 2 experienced math teachers with extensive expertise in creating math MCQs for our human evaluation of errors. We find that teacher-written errors and DiVERT-generated errors are similar in quality, and both are better than errors from GPT-4o. From our qualitative error analysis, we find cases that while the generated errors are plausible, the generated distractors are inconsistent and do not correspond to the errors. We publicly release our code on GitHub. Thank you very much for listening.